Anyhow, what I was saying is by the end of the day, all the lectures will be up online videos, and the whiteboards, they should already be there. But if they're not, let me know. Maybe there was an issue uploading them. Does anybody have any questions or anything before we begin? At all? Comments, concerns? All right. Well, that being said, let's pick up where we left off. And it was with what's called the normal distribution. So what we did is we introduced what's called the standard normal distribution, and it looks like this. And in sort of a scary way, let's call it F, and we'll use the variable Z instead of X. And it's given by this scary sort of formula. So again, I know, look, I said this last class, every one of these symbols in this formula you have seen before. I'm not saying that you need to not be afraid of this. It's a scary looking creature. It's got some exponents, it's got pi, it's got this square root, it's got this letter E. These are all things that at some point you came across in a math class, probably very briefly and without a very good explanation. And that's okay. What we need you to do is we just need you to understand that there's this thing called the normal distribution. You do not have to memorize this. Now, if you want to, you can, but you're not going to be asked to repeat it on a test or anything from memory. So why is this thing useful? It's useful because many things in the world we live in sort of, I don't want to say adhere to it, but this is a good model for many things. And the reason for that is because of its graph. So if I sort of briefly sketch what the graph looks like. Looks like this. So the graph is what's called a bell curve, which you've probably heard that term or phrase before. Anyhow, so we said a bunch about this last class, and what we'd like to know is we'd like to know how to use it for applications. So to use it, so what we do is we calculate the area, quote unquote, under the curve. So I mentioned this to you last week. So to explain in details what that means requires more math. You have to take at least a semester or two of calculus before you would even have a clue what that meant. And of course, we don't expect you to know any calculus right now. So what we do is we take advantage of technology. So in this class, we have options for doing this. So we can get so how can we compute this area under the curve? We can do this with calculus, calculators, and tables. Now in this class, we're not using calculus, so let's just ignore the fact that I even wrote this down, because we don't use calculus in this level of probability. So essentially, there's going to be two ways in which you should be able to calculate these areas. You're going to calculate these areas either using technology, whether you have a calculator or an application on your phone or an application on the internet. Free, of course, don't pay for anything. Or you can use tables. The back of your textbook has a table. And what I'll do is, I think I shared this with you last week, is I'll put some links up to some good ways, some, sort of ways for you to learn how to do this, because it is something you should know how to do, because we're going to do a bunch of examples with it. Does anybody have a question? Now, let me label a few points here because it's actually important. So that point is the point 0, 1. Or excuse me, not 0, 1, but 0. When I plug 0 into, if I go to the previous page, look at this function. If you plug 0 in for z, you get a number times e to the 0. And everything, you might remember, if you take a positive number and raise it to the power 0, it spits out 1. That's our definition of the exponent 0. And so what you end up getting is that this point right here is the point 0, 1 over square root of 2 pi. That's sloppy. Let's fix that. So on the next page, we'll talk about how we compute these areas. So does anybody have a question before I go to the next slide? / whiteboard. Okay. So here is our definitions. So what is the probability that we have some random variable? Let's say, let's be even a little easier. Let's just pick some numbers for now. So let's ask ourselves, what's the probability that, say, z is less than some number a? So what is this equal to? Let's write this out in English. So this is the probability. The random variable z is less than the number a. And what this equals is, this is going to equal the area under the curve up to a. So for those of you who remember interval notation, you might remember we can write this the interval -infinity to a. So if we go to the next page and do that, we'll draw this nice and big. And please, if you have any questions, stop me at any time. I have a feeling this is very confusing for most people. The reason I have that feeling is because when I tried to learn this many years ago for the first time, it was confusing to me.
I do have one comment. On the previous slide, it said probability random variable z is than number.
Oh, yeah. That's a good point. We can't have that kind of shenanigans. Less than. Does that make sense?
Yeah, that's good.
So that's a less than sign in there. My apologies.
Okay.
Thank you for pointing that out. Yes,
I didn't even notice. My brain just automatically saw less than
well, that's
in there.
probably why I didn't write it down, because my brain saw it and then it just wasn't thinking. I apologize for that. This is hard to do. I hate doing this like in this fashion. Okay.
What about one of your comments about like saying that like it's probably hard for some of us?
Yeah.
Like with that comment, you should just like teach it like we're a bit stupider than you think we are.
No, I'm not saying that. Wait, how did I?
I'm not saying that you said that.
I am telling you that it was hard for me to learn. That's what my point is. So look, I mean, it goes without saying. I've said this to you guys numerous times, whether you heard me or not. Learning most of this stuff is not easy. I don't care how smart you are or how hard you work. Learning it is difficult. Now, the time that it takes each individual to learn it, how much work each one of us has to put in, is going to be different. Some of us can get it easier than others, or quicker, as they say. But for most human beings, it's a struggle to learn this, particularly if you want to learn it. There's a difference between learning these ideas, and there's a difference between being able to do examples. And I would caution, even though being able to get examples done usually gets you a good grade in a class, that doesn't help you later on. What helps you later on is if you understand what's happening. The problem is that's the most difficult part. So, don't get, the reason I say that, Liam, is I don't want you guys to get discouraged. A lot of us try something once or twice and we feel like we'll never figure it out, so we just give up. And I don't really want you guys to do that. Now, of course, some of you will, but I will plead with you not to. All right, so let's draw another example. Oh boy, my curve started getting a little, oh, you jerk. This is one of them things that never happens in a classroom. So let's imagine we have our curve. Looks something, I don't know what's happening. It's like my pen is malfunctioning. Let me clean this up.
It's technology. What do you expect?
Yeah, this thing, oh boy, this thing's actually pretty good, this pen. I was very impressed by this thing I'm using, this notepad slash pen thing. So let me try to clean this up a little bit. Whoa. Come on, level out for me, honey. Oh my God. All right, so bear with me. I'm trying to become an artist here, and it's not as easy as I thought. So you might remember in a math class, there's these things called asymptotes, and that's what we have happening over here and over here. This blue curve just keeps getting closer and closer to the z-axis. It's not going to touch the z-axis, but it keeps getting closer and closer. So this is our z-axis. And what we want to do is let's pick some number a. I don't care where it is. Maybe it's right here. And so what I'm saying is if we were somehow able to compute the area of this shaded region, which I'm sort of coloring in. like this. So the area of this red region this is actually equal to the probability that Z is less than A. Now, what I'm going to do is I'm going to show you something that's in the back of your book, but it's also all over the internet. Before I do that, does anybody have a question? Comment? All right, let's do another one. Let's make a comment actually very quickly. So using symmetry, that's a very symmetric graph. Or properties of probability. What if we wanted to do the probability that Z was greater than A? Well, that could just be the following. It could be 1 minus the probability that Z is less than A, because we'll take the complement. Remember this idea of a complement? Or if you want, if you go back to this picture, the idea, I haven't really, I mean, it's impossible for me to draw perfect, but the idea is that this bell curve is perfectly symmetric. I pointed that out last week. And so the area from A on would be the same as the area up to negative A. So let's, you know, you might have to have your brain sort of do some thinking about this. So if I wanted to know the probability that Z was greater than A, another way I could define it is the same thing as the probability that Z is less than negative A. So this comes from, let's write down where both of these things come from. So I'm going to write up here, this is the idea of the complement right here. So let's call that, this is using the complement. And this is just using symmetry. So on the next page, I'd like to draw that so you can sort of understand what I mean. And again, at any point, if you have a question or a concern, just yell it out or type it up. I like to think in my head, at least, that those of you who can are trying really hard to learn this still. Although I understand that many of you might not even have, you know, if you're anything like me, like I'm down here in my like my, what do they call this in your house? Your game room or your family room, which, and I got kids upstairs rowdy. I got a washer and dryer running. I got Mickey Mouse on the TV. This is not exactly optimal learning environments. I'm sure some of you have it similar or maybe worse, or maybe some of you have it better, where you just have your own little office to learn. I don't know. I don't have that. The kids have taken over the house. Okay, so let's draw that picture one more time, just because it's fun to draw these things. I need practice, as you guys know. I'm getting I'm getting better. So let's take our point, which I'll call A. Give it, call this green. So if this is A, then the same distance over here, this would be negative A. And so this region, this area, and this area so what is this region? This is the area under this curve. So this is the probability Z is greater than A. This is the probability Z is less than negative A. And these two things are equal. All right, does anybody have a question? Okay, so the last thing this tells us, and I know I sort of pointed to this last week, but it's worth reporting. So lastly, we have, what is the probability that Z is between two values? Not just greater than 1, not just less than 1, but what is the probability that A is less than Z is less than B? Well, this is just the area under the curve between A and B. My marker is acting up. So if I just draw that real quickly, because why not? So we'll draw this guy in purple, because purple's. So if here's our normal distribution curve, our bell curve, let's pick any 2 points. I don't care what they are. We'll call this one A, we'll call this one B. And they don't have to necessarily be positive and negative like I've drawn them. That's just one example. So this green region is the area under the curve between A and B. So take a moment. If you have a question, we're going to do some examples right now. So if you have any questions, let me know. Okay, so what's one way to do this? Well, one way to do this is the following. So what I'm going to do is I'm going to share a web page with you. Hopefully you can see it. I just got to find which one it is. All right, you guys should see a web page right now. Hopefully you do.
I'm still not seeing the web page.
You're not? Are you seeing it now?
Yes,
See
I
like
am.
Roach's web page, the intranet. Good. Okay, so
Yep, correct.
one way to do this by hand is to go to this intranet and just type Z table. So the way we call this Z table. And if I click this in, the first thing you'll see is a bunch of tables. And if you click on one of them, you'll start to see what I've been blabbering about. And you have these numbers. And what you have to do is you have to think about how can I read this table. So first off, again, let me repeat this. If you Google Z table, a bunch of this kind of stuff pops up. And which, so the first question is, how do you read these tables? Well, every one of them is slightly different. You'll see that this table is giving us a slightly different area than what I described. Now, neither of us is wrong. We're just doing it differently. If you look at their bell curve right here, you'll notice that they're just computing the area from 0 up to Z. So in order to use their table, you would have to actually get their number and then add 1/2 to it. That might not make sense to you right now, but I'll explain why in a second. Remember, the full area under the curve is 1. So the area up to 0 is 1/2. So if we go back, if we cancel this one, maybe we look at a different one. Here's a different table. This table starts like we described it. It takes your Z values and it gives you the area from infinity, negative infinity up to Z. So let's show you how you might use this table. Is it still there? You didn't lose it, right?
Yeah,
Still see it?
still there.
All right, good. Okay, so let's get back and do an example. So am I able? So let's do an example of this. So let me switch colors because I don't like green. So what I want to do is I want to compute the probability that Z is less than, let's say, 0.62 using a what they call Z table. Or some people call these Z scores. So I'm just giving you these names. If you want to Google them and learn more or why, that's fine too. Okay, so here's how we do it. I'm going to write this out. Hopefully it this works. Trying to get both of these windows up at the same time. Let me see if I can do that. Bear with me a second. It's not letting me do it. All right, I can't figure out how to do this. I wanted to show both screens at the same time. It's not letting me. I'll have to figure that out. I should have done that beforehand. My apologies. Okay, so anyhow, we have the problem at hand. So how are we going to do this? So let me come back to this and let's explain how we're going to solve it. So let's Google z-table. Or open to the table in the back of the book. I don't care how you do it. So I'm just going to use, since I already have this web page up, I'm going to use this one. And I will share it with you right now. So what you should be seeing is you should be seeing this Z table. And what I'm going to do is remind you that these numbers in these tables, what they represent is different areas under the curve. Now, what we were interested in is we were interested in, I believe, what was it, 0.62, I believe. So what we have to do is we first look down. You'll notice that the horizontal column represents what we call the 100th place, the hundredths, and the vertical column represents the tenths. So we wanted 0.62. So if I get my marker out here and I come down here, I need to look at this row where there's a 0.6, and then I need to look at this column where it's 0.2. And I need to come down this column and come across this row until they meet, and where they meet is at this value, 0.7324. So let me repeat this. For those keeping score at home, the number we were interested in is we were interested in the following. Let me write it over here. We wanted the probability, I believe, unless I made a typo. We wanted the probability that Z is less than, why is it not letting me write there? Come over here. We're interested in the probability that Z was less than 0.62. And what we discovered is that that's equal to 0.7324. So if we go back to our whiteboard, what we found is we found the probability that Z was less than 0.62 was equal to 0.7324. Does anybody have a question or comment?
That's why these classes are getting smaller and smaller each class.
What do you mean, the number of attendees?
Yeah.
Where we at 8? Well, we just assume that everybody has other issues.
And they didn't have issues before when it was in the classroom?
Yeah, you never know. Okay, so that's one way to answer this. Here's another way, and you should know how to do both just for the sake of doing it. But it is 2020, so an alternative way So if you just Google Z-table calculators, you're going to find lots of lots of apps. Here's the one. Let me get it up before I show it to you. La 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 la. Where did it go? Problem with these web pages is they all have advertisements everywhere. And I want a simple one. Here we go. So if I go to so there's lots of free ones. So you can just Google Z calculator, Z table calculator. So if I share this screen, here's one. All I did is I'll just show you, if I Google Z table calculator, and in true O'Grady fashion, I don't even spell it correctly. But the first hit that comes up is this calculator.net. And don't worry about the top part yet, but all you have to do is worry about the bottom one. What we're interested in is the probability that Z is less than something. So we wanted 0.62. And so if we plug that in and calculate it, you'll see that it gives us the answers above it. In particular, the answer we got before was this one. This was the one we asked you about. And it's 0.73237. Or if you round it up, you get what we got, 7324. Does anybody have a question about this? All right, someone's typing. This is always good.
I misspelled a word, but you get the idea.
If you want Chrome, so what are you saying? If you
do you have like a Chrome in the quick access?
Yeah.
Yeah, right click it and then click the one that says Google Chrome.
Okay, well, I just type in I always just type right up here.
Should be by tasks. Well, I mean, so you can show two windows at the same time.
Wait, say that again?
So you can show two windows at the same time, the dilemma you had a while back?
Yeah, how do I do that? Is that through Google or is that through Zoom?
Well, for when you're trying to share a screen.
Yeah.
Yeah, like
when I go
whenever.
To share, it doesn't give me the option of split screens right now. I don't know why. It should.
Oh, you're talking about showing your whiteboard and this.
Yeah, I want to show those at the same time. Yeah, I can easily show you two web pages. That's not what I want to do though.
Oh,
I want to
okay.
show the whiteboard, and it won't. There's got to be a way to do it, but I just haven't figured it out. Anyhow, that's how you do these things. So you want to get practice with that. Again, you could probably, your calculator, if you have a calculator, it probably does it. There's lots of good free apps. I'm sure you could, if you play around for 20 minutes, you'll find one that's easy to learn. But you will have a fair amount of you will have a fair amount of these to answers. Does anybody have a question about how to compute these numbers, at least? Okay, so that was what we call sort of the easy case. Now we have to sort of write things a little scarier. So what we talked about so far is what's called the standard normal distribution. And what we want to do now is talk about what we call the general, the normal distribution in general. So we now turn to the more general so the more general problem is what's called the normal distribution. Not the standard one. This one doesn't have an adjective in front. This is just called the normal distribution. So what is the normal distribution? Well, it's given by the following. So now the function, we'll use the variable x to distinguish it. Now this is going to look very, very frightening. We have 1 over Greek sigma. You guys know what this letter is. We've seen it before. 2 pi. And then it's going to look very similar. You have this exponent of -1/2. But now this is a very scary creature. It's x minus mu over sigma quantity squared. Yikes. Talk about scary. So. Okay, so what are these letters we have? Well, we say this has mean, mu, and what was standard deviation and variance? Well, so we always use sigma to represent the standard deviation. So here's what you should to note. The standard one, standard normal distribution, that's just has mean 0 and standard deviation 1. So it's just a special case. All right. So now, if you're afraid right now that you have to learn this scary thing, you don't. Now, if you want to, by all means, you can. But there's some very good news. And it's this big fancy theorem. We're not going to state it, but it's a beautiful, beautiful thing. And so it's going to save you guys a lot of headaches. Excuse me. So this is good news. We can, quote unquote, make any normal distribution a standard one. How do we do that? We do the following. Remember, Z is for standard and then X is just for normal. But if we use this little equation, we can take any normal distribution and write it as a standard one. And that's useful because all those tables are written in Z, so we can easily do this. This shouldn't shock you, though, for the following ways. So let's write this down a little more carefully using probabilities. We change color. We just let's get that purple. I like this purple. It's cute. So that is the probability that, say, X is between A and B. Well, you can use some calculus, and we don't care about that here, but we can write this as the probability that Z is less than B minus U over sigma, and Z is greater than A minus mu. Now, let me clean that up. That's ugly. So this looks scary, but remember, these are all going to be just numbers. So these things that look like fractions downstairs, you're not going to be frightened by them because they're just going to be numbers. Because if A and B are numbers and mu and sigma are numbers, you're just going to have numbers. So there's nothing to be like overly afraid of. No one's going to ask you to solve crazy equations. So you don't have to like super duper stress over that. So let's do an example. Before I do that, does anybody have a question? Going once, going twice. Does anybody? All right, so we know how to find Z values. That's good. Very, very good. Now the question is, how do you find values that are normally distributed that aren't Z values? So let's do an example of that. And please stop me if you have any questions. I'd be happy to answer them. So let's assume X has normal distribution. With a certain mean, let's say, I don't know, let's say 5.2. And let's say that the standard deviation is 0.3. What we want to do is we want to compute the probability that X is between certain values. So let's compute the probability that X is less than, say, 5.4. So we can't just go straight to the table because this is not a Z variable. We don't have mean 0 and standard deviation 1. So let's make a note of that so we don't end up driving ourselves crazy. So we need to first convert X to Z. And so we gave you that formula. So what is Z? Z is equal to X minus mu over sigma. What does this become? Well, this is X is 5.4. That's the one we're interested in. Minus 5.2 over 0.3. So you get 0.2 over 0.3, which is nothing more than 0.67. So I plug in my mu, I plug in my sigma, and then what is the X value I'm interested in? Well, I'm interested in what's happening before 5.4, so I can just plug that into my formula. And so what this tells us is it tells us the following. So let me make this very clear before I go to the next page. What we're saying is the following, is we're saying this. We're saying the probability that X is less than 5.4 is the same as the probability that Z is less than 0.67. That's what we're saying. So that's very similar to what we did before. So what do? We use a table or a calculator. So we get that the original X is less than 5.4, which we just determined is the same as Z less than 0.67. When we plug that in, we get 0.74857. Does anybody have a question about this? Any questions, comments?
All I know is it's so much writing what we have to do, and it confuses me completely.
Oh, Liam. What else is there to do? We're in quarantine.
Go out and try to get it so you can die sooner.
Oh my God, Liam, why would you say that?
Because I have no filter.
This is true, you do not. You do not. Let's fix this we.
I personally feel like it's a better way to live.
Oh my God. Where do you come up with these ideas?
Would you rather me lie or be
I
honest?
suppose you're entitled to your opinion. This is true. I suppose. All right. So, you might ask, okay, so let's rephrase this problem into a real world scenario. And we'll do that as a last thing before we pass along here. So you might be asking, like, okay, so what is this stuff used for? Who cares? So we could have as a real world example. I'll put real world in quotations. So what do I mean by that? Well, suppose I just phrase the problem in context. What do I mean in context? So on average, adults have, say, 5.2 liters of blood. So we're saying, let's assume we went and we tested 1,000 or 20,000 or 50,000. We took some large group of adults and tested how much blood they had in them at any given time. And let's assume on average they have 5.2. So this is something that maybe doctors and hospitals keep track of. So now we're going to say that an adult, we're going to have this random variable that an adult has X amount of liters of blood in them. So assume this is normally distributed with mean equal, well, no, the mean would be the average 5.2 and standard deviation could be 0.3. How would we know this? Well, we showed you a long time ago how to calculate this. I mean, we showed you way long ago, if you have a bunch of data, how do you calculate the mean and how do you calculate the standard deviation? We showed you this. You did this on like homework too. So imagine a study where a bunch of healthcare people go and they say, okay, let's go determine the average amount of blood in an adult. And then we take all our data, we get the average is 5.2. Remember, we had a name for this. There was these different things. We had population, mean, and we had these terms. And then we go and we do the data and we get this. And so what we'd like to know is the following is determine the percentage of adults who have less than 5.4 liters. And so what we showed, our calculation shows, if you go back a couple slides, what did we get? We got that the probability is 0.7485. So what we could say is we can easily say that 74 point, if you round up, 86% of adults have less than 5.4 liters. Not litters, liters. They're not cats that are procreating.
Maybe they are.
They could be. Well, that's a good problem right there. On average, how many every time a cat gives birth, how many are in the litter? We can ask the tiger, or the Tiger King. We can go see what it's all about.
Or how you worded it, every time a human gives birth, how many of them end up being cats?
How many cats? Well, that would be 0, I would think. Then again, it depends on your how you want to do it, I guess. Okay.
There are some sick people.
Well, this is true. There definitely are. All right. Does anybody have a question about this? Going once. Going twice. All right. So what we'd like to do is we would like to ask, you're not going to really learn this unless you do it on your own. So we'll give you some problems. Hopefully you'll work on them before Thursday, and then we can help give you any answers or give you some help on Thursday if you have any. Okay. So right now we're saying, here's the thing. All we know how to do right now is we know how to answer questions if we assume things are distributed normally. Now, that's not always a good assumption. You just can't assume things, but many things turn out to be normally distributed. One of them is the amount of blood in an adult. Other things that tend to be distributed normally are things like height of adults. And you can go on and find examples in our world that behave normally, or at least resemble normal behavior. Not everything, but some things do. So remember what our ultimate goal is mathematicians and probabilists and statisticians. Our goal is to sort of model the real world and sort of try to predict as best we can. It's not always perfect, but what we're trying to do is determine when our methods are valid and when they're not. And if they are valid, how accurate are they? So right now, we're just in the very beginning of all this. If you have questions, I'll take them. Otherwise, I say I'm going to stop the recording, and I will save these slides and upload them. If you guys have questions, speak now. If not, I will hopefully hear or see you guys Thursday. All right. Be safe. And